Welcome to Lecture 12. This will be the last lecture in Unit 4 and also the last lecture in Weather Prediction 1. I want to do something kind of fun, look at a hole punch cloud situation and a mesovortex that formed over Lake Ontario. This happened a few years ago, but I was very fascinated by this event. And when it occurred, I thought to myself, well, why did this happen? All right, everyone was talking about it. Oh, look at this cool mesovortex over Lake Ontario. And just me, the way I am, I'm kind of like, well, what caused that? Yeah, that's cool, and I really like to see that, but I want to know why that happened. So that kind of goes into forensic meteorology. If I ever did get a PhD, this is definitely what I would do, especially on the meso and micro scale events. All right, more of a challenge to me on those, and sometimes you don't find the answer. But on this one, I think I was able to find pretty much most of the answer with it. All right, so one thing I always teach you with forecasting is go back, try to figure out why something happened. And even in something like this, when you see something cool, go try to see why it happened the way it did. All right. And it's kind of like the CSI show, which I talked about before, but with weather. All right. And, instead of criminal investigation, you're basically investigating what happened. And you kind of like look at it like you're in the courtroom, you're a lawyer, and the models are lying to you, or things are lying to you, and you're trying to figure out where it's lying, or even if it's not lying, you're trying to figure out the timeline and exactly what happened. And a lot of people that are involved in forensic meteorology do very, very well. You get called in the courtroom, and you're doing briefings and things like that, or different, cases for different, I don't know, insurance companies or corporations or whatever. You can make a lot of money doing this. We're talking $500 plus an hour for some of these people to do this. All right. So, again, I don't do this for the money. I do it because I love it. But still, if this is something you're interested in, it can be a very high paying job if you find the right path. All right. So, I'm going to show you the video of this and kind of show you the sequence. And then I'm going to show you the video again at the end. That way, you kind of have the video, fresh in your mind at the beginning, and then we'll watch it again at the end. All right, it's gonna make a lot more sense at the end. Really cool thing. This is from CIMSS. They have an awesome website and then also a great Twitter handle with all sorts of cool satellite stuff. So if you're interested in that, definitely check it out. They did a blog post on this. They didn't talk about exactly why it happened. They just talked about, hey, look, here's the mesovortex, and that's what kind of made me search what did happen. All right, so let's take a look at this here. Pretty cool. You see these clouds, thin layer clouds, and then you start seeing these holes start to form, right? And as these holes form up, what happens? The sun comes out, and then look at this mesovortex that can spin up really quickly. And then it goes over this ice and it dissipates, right? So look at the water here. You see the water is open here, and I'm going to show you the water temps were pushing about 38 degrees in some of the deeper portions. And then it's interesting as the mesovortex moves over the ice, it completely dissipates. And I'm going to talk about that. It has to do with the gradient. And then those holes you see at the beginning, those are the hole punch clouds, which are caused by planes. And we'll break that down as well. And we're going to look at this whole sequence of events and what likely caused this to occur. And sometimes when these things form, especially when they come on shore, you can get a couple inches of snow really quickly. All right, so while not overly common, they do occur. And, we're going to break this down and kind of look at it. So you kind of have that in your mind. We'll watch it one more time. You see the holes form, the sun comes out, air starts to mix. Here comes your mesovortex. It forms over that gradient here. Then it loses that gradient over the ice, and then it dissipates. All right, so let's kind of break this down and look at it the best we can. All right, so I put some infrared images in there, and then we're going to move into visible. But let's ask ourselves a few questions. Why did this happen? Did the hole punch fall streak holes cause this, or was it a part of it? Was it the main reason or part of several reasons? And, let's just break this down. Again, this is just for fun. It's a fun thing to do, and it's a good habit to get into to become a better forecaster. So you got your infrared. You're not really getting a whole lot of information on that, and this is a wider view. Not the highest resolution, back from 2015. But if you look at the visible, and we're going to focus here in this area here in Lake Ontario, watch from the larger scale, watch this occur. You see the holes form. You see the mesovortex start to form there. You see it move across Lake Ontario, and then it moves back over the ice and it dissipates. All right, so you can see that from a wider view, but then of course I give you the video of the closer view, and then here's even more up close, much better resolution here. This is from CIMSS, and you see that form. I mean, what does it look like? It looks like a tiny hurricane. All right. You know what it kind of reminds me of? It reminds me of Cyclone Tracy from back in Australia. I think it was on Christmas Day back in the 70s, I believe. I can't remember the exact date. Maybe early 70s, somewhere around there. But it almost looks like a tiny cyclone. Yeah, and it's kind of interesting to watch that progression and moves over the ice there, and then it breaks up. So first, what are hole punch clouds or fall streak holes? What is it? Well, it's when a large number of ice crystals in a cloud form at a fast rate, basically starting a domino effect of evaporation, which creates a hole. You'll hear many people refer to it as a domino effect of evaporation, all right? So, a large amount of crystals form in the cloud, they form at a very fast rate, and they start this domino effect of evaporation, which starts to cause the hole to open up. So when you talk about planes or aircraft, passing aircraft and planes have a large reduction in pressure behind the wing. The air expands. This can cool the air quickly and can lead to more ice formation. Sometimes you can see the air cool up to 20 degrees Celsius, and especially in these larger planes and bigger aircraft, you can get more air expansion and more cooling. All right, so it's really interesting. These planes will move through the clouds, and a couple things are going on. Maybe you're not quite cold enough to form ice crystals, but this can help cool it off to get the ice crystals. Or you are cold enough, but you don't really have the nuclei present to get ice crystals. And that's the other factor with this. What's another huge reason for this besides lowering the pressure and causing the air to cool very quickly? The plane adds pollutants to the atmosphere. These pollutants activate ice nuclei. Okay, so this pollutant that wasn't present is now present in the cloud, and it activates ice nuclei. This goes back to some of the basics with precip types. You have to have some sort of nuclei for the ice nuclei to form on and to activate. Okay, so we know there's super cold water that eventually can turn into ice crystals. But if you don't have the nuclei and you don't get cold enough, then it's not going to form into ice. All right, that's why. If you're not at -10 or you don't have the nuclei, then you're not going to get ice crystal formation. And going back to, precip type, you're not going to get snow and sleet. Now, we're not talking about this, snow and sleet with this type of stuff because it's such a thin layer of moisture that it evaporates rapidly and just dissipates. But the key is it cools it, and sometimes that's the trigger, or in other, probably more likely, it adds pollutants to the atmosphere, and these pollutants activate ice nuclei. And this goes back to -10 degrees Celsius in the snow growth region, which we've talked about a lot. We know that -10 is a safe bet, why we use that temp and it feels safe with it. Majority of ice nucleation occurs close to -10. We know -12 to -18 is the prime reason. But keep in mind, each nuclei is unique. Remember, I talked about some can maybe form as warm as -6, -7, -8. So that's something else to keep in mind. These planes that form new nuclei that's not present before, the pollutants, there's all different types of nuclei. You got dust nuclei, clay, pollen, pollutants. So there's all different types of ones. There's sea salt, there's sulfate from volcanoes. There's many other, all right? So keep it simple. The plane causes a lowering of pressure. Again, going back to that really quickly. You have a large reduction in pressure behind the wing, air expands, everything cools, or, which is more likely to me, especially in this circumstance because it was already cold enough, it was adding pollutants to the atmosphere. These pollutants activate ice nuclei, and that caused these ice nuclei to form, and what happens, they're more dense, and they fall into drier air, and they evaporate. I'm going to show you that in detail, especially when we look at the soundings. So here's some cool pictures. I've seen from different government sites and, different weather services and places like that. You can see the holes start to form here, and you see those ice crystal formation, and what happens, it falls into a layer below it that's dry, and it evaporates at a fast rate, okay? Here's another really pretty example of that. You see the clouds form, or the hole form here, and the ice crystals start to form and they're more dense and they fall into their drier air and they start to evaporate and you get these holes. Okay, another beautiful one here. But keep in mind they're not always perfect holes, right? And sometimes it's not just one, there's multiple ones because multiple planes are going through. Here, you're going to have planes coming at angles, so you kind of get more of this ribbon look to it here. You can see the trailing with that. You can see it cutting through the cloud here. It's not always going to be perfect circles, all right? You can get them to look like this as well. But still, this would be a hole punch. Not a perfect circle here, obviously, but you can see where it was trailing through, where it activated the ice crystals, where the ice crystals fell and then evaporated, and then a large area starts opening up. Sometimes they're more perfect circles, sometimes they're more trails, okay? So there's no exact way that these form, and sometimes there's multiple ones of them, which actually in this event you saw. You saw multiple holes start to open up. Here's a really beautiful one. It's almost like a sundog. As those ice crystals are falling, they're refracting off the sunlight and making a rainbow. Very, very beautiful. I mean, shoot. Just seeing a fall streak hole is cool enough. To see something like that is pretty amazing. All right, so why was there even an alto cumulus deck even there, all right? So you can have cirrus cumulus decks, you can have alto cumulus decks, but they're usually thin, fairly thin decks of clouds, right? Because if it's super thick, it's going to be hard for the plane to open a hole in something like that. It has to be relatively thin, all right? And if you look at the sounding from Buffalo, what do you see? Well, I mean, pretty obvious where that cloud deck is, right? Look how saturated it is right here, okay? So here's your cloud deck, and what do you have? You got a little bit of an inversion going on here. You have a couple actually going on, but you got dry air above, and most importantly, you got a lot of dry air below, right? So as this plane flies through the cloud deck, and obviously in this situation it's plenty cold enough, and it adds pollutants to the atmosphere that activate these ice nuclei in a very thin layer, right? Normally, they're not going to activate in such a thin layer of moisture, but with the plane adding the pollutants, the nuclei to it, you're getting this activation, and as these ice crystals fall, they immediately evaporate into this dry area below, and then the hole starts to open up. Later on the day, I mean, the moisture wasn't quite as pronounced in this little small pocket, but I would argue maybe the cloud thickened a little bit here, and of course, obviously, what's happening at this point, you start getting dark, so you're not going to be able to see those hole punches as near as well. You can see them on infrared, but visible, obviously, is a lot easier to see them. All right, so why are the winds converging over Lake Ontario? Okay, so we know the plane's flying through the cloud, and it's causing holes in the cloud. Well, what does that do? Well, if you're getting enough of these holes, it opens a bigger pocket, and now the sun is shining, right? And what happens when the sun starts coming out in the morning and starts hitting the ground? You start getting mixing, right? You need the sun to activate the mixing, all right? So, I mean, you can get movement of air without the sun, obviously, but the sun helps kind of, it's like the push. It's like the snowball being pushed down the mountain. It was the initial push, all right? So why now? We know what the initial push of it was, but what is causing the convergence over Lake Ontario? Well, let's look at where Lake Ontario is. Here's Lake Ontario, and then here's Lake Erie. Well, look how cold these temps are. -6, -16, -9, -17, -8, -9, -6, -4. This is some cold air, all right? And over Lake Ontario, I'm going to show you, it was as warm as 38 degrees, okay? So there's a huge gradient going on here. So what's starting to happen? You see kind of this circulation starting to form around the lake here. Obviously not perfect, but you can see almost like a low starting to form. Well, why is that happening? Well, this water, compared to the land, is relatively warm, all right? This goes back to lake effect snow. And this cold air is what? Higher pressure, right? And what's this warmer water here? Lower pressure. And what's the air doing? High to low. And you're starting to get this circulation that starts to form, all right? So this is going to lead to the mesovortex starting to form. But then you might ask yourself, well, look at Lake Erie. I'm not seeing that convergence. Why is it happening over Lake Ontario, but it's not happening over Lake Erie, even though you could argue the temps are just as cold, if not colder? Well, Lake Erie is much more shallow than Lake Ontario, and by this point, Lake Erie was completely frozen over. So because it was completely frozen over, yeah, it might be a tad bit warmer over here, but because it's just a block of ice, you don't have that gradient going on. We're here in Lake Ontario, while yes, this part was frozen over, and you can kind of see, you don't have as much of that turning into it. But where the water is warmest, you see that convergence. You see that high to low over Lake Erie there, or not Lake Erie, Lake Ontario here. So I'll show you more details with that. So that's the first thing I kind of noticed. And at first I was a little tripped up by this. I was like, wait a minute. But then I thought, oh, wait. Yeah, Lake Erie's frozen over. That's why you're not getting it. So it's kind of cool. So let's go in time. You still have that nice convergence over Lake Ontario. But what happens is we start going through the day and the air temps start to warm. Well, you start losing that convergence, all right? Now, when this mesovortex moved over the ice, what also happened? You lost that gradient from the lower pressure, the warmer water in Lake Ontario, compared to the higher pressure and the colder air over the land around it, right? So when the mesovortex moved over the ice, it lost that gradient and then it dissipated, all right? So that's another factor that's going on. But as we go through the day, look at that. You see that gradient kind of really dissipates? Well, it's because it's warming up. Now we're 17, 14, 16. I mean, again, colder, but nowhere near like what we were seeing. So the gradient starts to dissipate, and you don't have the same convergence over Lake Ontario. So pretty interesting with that. So Lake Erie versus Lake Ontario. Why is Lake Erie frozen, but Lake Ontario is not? Talked about that. Lake Erie is much more shallow, so it freezes a lot easier. And, again, the air temps were just as cold, not colder, but you had to know that Lake Erie was frozen over. That's why they weren't converging. So here's Lake Erie. Again, you can get a lot of this from NOAA and National Weather Service offices out there have these charts. They have a great buoy network. And then, obviously, visible satellite imagery is going to make it pretty obvious if the lake is completely frozen over, right? So it's completely frozen over. You can see that here. Whereas Lake Ontario, you see what I mean? 38 degrees, 38 degrees. Now, it is some ice over here, and that's where it lost that gradient. But still, it's deep enough, and there's still enough relative warm water that you get that convergence, okay? Here's Lake Erie. This was really close to New Year's, so about a month and a half before this event. Then this is at the time of the event. It's completely frozen over. It's just a block of ice, so no gradient. All right, where Lake Ontario, you did have that gradient, right? So, again, hole punch opens up, sun comes out, mixing starts, air starts to move, air is moving towards this lake, the air is converging over the lake, mesovortex forms, and then the mesovortex eventually moves towards the ice, loses that gradient, dissipates, right? Well, was that it? Is there anything else? Well, another thing you want to do is look at the air aloft, all right? So you only need a 13-degree temperature difference between the water and 850 to get lake effect snow, okay? So we know that from the lake effect snow lecture. In this case, our 850 temps were about minus 18 degrees or close to 0 degrees Fahrenheit, where the water temps in Lake Ontario range from about 38 to 34 or 3 to 1 degree Celsius. So there was a 20-degree difference between the lake temp and 850 millibars, all right? So there's a lot of rising motion. So not only do you have the gradient at the surface, you have an incredible lapse rate where the air is going to rise in the vertical as well, okay? So Lake Erie is frozen over, no more temp gradient, rising motion off the water. Yeah, it's probably a little bit warmer over that ice. It's maybe not quite as cold as the land, but there's not much of a gradient there, okay? You do have the gradient aloft, all right, but you don't have the gradient at the surface. And even the gradient aloft is not as pronounced over Lake Erie. Why? Because, again, the lake is frozen over, where over Lake Ontario is 38 degrees, right? All right, so that's a big factor with this as well. So you lose that lack of convergence, and Lake Erie is frozen over, so you don't have the same lapse rate. Early versus late season. If this was earlier in the season, maybe November, December, and Lake Erie was not completely frozen over, maybe this could have occurred there, and they do occur in Lake Erie. It does happen there as well. All right, so here it is, minus 18 degrees Celsius aloft at 850. So you have really steep lapse rates, a lot of cold air aloft, and that helped everything rise into the vertical as well. So you can see that progression. It stays pretty consistent as well. All right, so that was some pretty cold air. All right, so let's think of the sequence of how this works, okay? So you had low to mid-level alto cumulus cloud deck, right? There's lots of dry air above, but most importantly, there's a lot of dry air below and a little bit of capping, right? So that moisture's trapped. You got a thin layer of clouds. The plane flies through the clouds and causes mass crystal formation, new crystals because of the pollutants, the ice nuclei activate because of these pollutants. And what happens? They start to fall and evaporate because these ice crystals are more dense. They fall into this dry pocket of air. They evaporate. This does what? This causes the sun to come out and mixing to occur rapidly. And then you have relative warm water compared to the surrounding surface. All right, the sun comes out, you start getting mixing, and now this air starts to flow towards the lake. Right? Why? Because you have that gradient from the cold land to the warm water. All right, so you have the gradient of the surface, and also you have the gradient aloft. So it's not just the surface gradient, it's the gradient aloft with the higher lapse rates that enhances this convergence and uplift. The winds converge, all right, and they start to spin, and they initiate where the highest gradient is from the land to ice. So where that land and deeper water come together that was a little bit warmer, it formed over that area, and then it moved towards the ice, and as it moved towards the ice and lost the gradient, what happened? It dissipated, all right? So gradient of the surface and loft at 850 enhances the convergence and uplift. Winds converge, they start to spin, initiate where the highest gradient is from that land and ice, and then, eventually dissipates when it does get back over the ice. The moisture source, obviously Lake Ontario, all right? Similar to what? Lake effect snow. Obviously, this is nowhere near what lake effect snow can be, but the moisture source and the energy is coming from Lake Ontario. And nothing happens on Lake Erie because it's frozen over. Okay? So pretty cool, right? Again, it's one of those things, I saw it, I thought to myself, all right, what caused it? I'm just not one of those people that just look at something and go, okay, cool. I usually look at it and go, I wonder why that happened. And I kind of went back and tried to figure it out. Could I be missing a few things? Sure. I mean, there's no way that I'm going to sit here and say I know everything that happened and I have it perfectly. But I think I have a pretty good idea what happened, and it's pretty cool to kind of break it down. And that goes into the forensic meteorology. And this is how I would go about it if I was going into a courtroom and trying to explain what happened. All right. I think it's important to do. And even if you don't get into forensic meteorology, this is good to become a better forecaster, because this will force you to go back and look at things and try to see why it happened. All right, so now let's go back to that video. All right, so we had it at first. We went through everything. Now you're going to get the whole sequence, all right? So again, hole punch clouds, sun comes out, convergence over the water here. This is where that best gradient is, where the warmest water is. And then what happens? It goes over the ice, and it starts to dissipate, right? So again, planes, and why, one thing I should have added, what is over here? Toronto. Right? So that's a major airport, and that's why so many planes are taking off. They're probably flying towards, who knows, the East Coast or Europe. So this is why you're having so many hole punch clouds here, because you have a major international airport, okay? So that's something I should have added. So you got Toronto, planes are taking off, you got hole punch clouds forming, the sun comes out, convergence over the water, plus you have air rising in the vertical, you get your mesovortex, it eventually goes over the ice, the gradient is lost, and then you don't have your mesovortex anymore. This is why we never got it over Lake Erie, because it's completely frozen over. Pretty cool, all right? I know I'm a nerd on this type of stuff, but I still think it's pretty cool. And I'll leave all this, links and imagery for you so you can kind of look at it yourself. All right, so again, I just wanted to do something, kind of fun, a little bit different. And this is where we'll end with Unit 4. One thing I talked about at the beginning of the class, that weather prediction 1 leads right into weather prediction 2, and I almost consider it one continuous class. So in weather prediction 2, we will continue with a lot of other awesome topics. I'm trying my best to give you as many tips and topics as I possibly can, just to give you a good wide range of things to make you very versatile. One thing I pride myself on is maybe I'm not the best on one thing. I try to be really good at everything, but I look at it as if I can be good at lots of things, that just makes me more well-rounded, all right? So we will continue in weather prediction 2.